Hello everyone, my name is Ravina Raghunath and today we are all going to learn about an emerging memory technology known as Magneto-resistive Random Access Memory, commonly known as MRAM. Why are we all here to talk about MRAM? Moore's law is now facing a brick wall. There are several problems which limit miniaturization, such as leakage currents, such as sub-threshold leakage and gate leakage, which is a critical issue in CMOS. Second, fundamentally unavoidable thermal noise. Heat generated from an average workstation can go up to several megawatts. MRAM is a promising candidate to challenge the CMOS-dominated memory world with its high endurance to temperature, high speed performance, non-volatility, and low cost. Now let us discuss what is MRAM. MRAM uses magnetism rather than electrical bits to store your data. Therefore, there is no refresh cycles needed to store data. It uses electron spin in a ferromagnetic material, a material which is highly susceptible to magnetization to store bits of data and magnetoresistance to read the stored data. This is very useful for laptop and MP3 devices which require a longer battery life.
Now let us discuss why MRAM. DRAM is a type of memory where data is stored in the form of charge in a capacitor. It is a cheap memory and can be used for high-density applications. The disadvantage of DRAM is that it needs refresh cycles to store data, as data can be lost due to leakage of charge in a capacitor. SRAM is a static memory and can retain a value for as long as power is supplied. It is typically fast and can be used in caches for high speed. Disadvantage is the cost per memory cell is high. Flash memory can retain data even when the power is off. The only disadvantage is the rate at which data storage occurs is slow and it uses a lot of power. MRAM is an ideal device as it combines the best features of the three: the high density in DRAM, high speed of SRAM, and the non-volatility of flash memory.
Here is a comparison table of the features of MRAM with the features of other memory technologies. The other memory technologies here include SRAM, DRAM, and flash. The features compared here are the speeds of read and write, whether the memory is volatile or not, the endurance limit of all the memories, whether the memory requires refresh cycles or not, the cell size of the memories, and whether the memory works well in low voltage. The heart of MRAM lies in its magnetic tunnel junction. The magnetic tunnel junction consists of two layers of magnetic material such as cobalt iron separated by an ultra-thin layer of insulator, typically aluminum oxide with a thickness of 1 nanometer. The insulating layer is so thin that electrons can tunnel through the barrier if a bias voltage is applied between the two metal electrodes. In MTJs, the tunneling current depends upon the relative orientation of the magnetizations of the two ferromagnetic layers, which can be changed by an applied magnetic field. This phenomenon is called as tunneling magnetoresistance, TMR, which is a consequence of spin-dependent tunneling. Structure of MRAM. Can anybody guess? The three-layer synthetic antiferromagnet fixed structure helps in gaining a magnetically rigid system and helps in controlling the magnetic coupling to the free layer. The read process is quite simple. During the read operation, the transistor is in on state. The current is flown through the MTJ and the resistance due to the current is measured. If the resistance is high and the magnetization is in anti-parallel direction, the digital value 0 is read. If the resistance is low and the magnetization is in parallel direction, the digital value 1 is read. How to write to an MRAM? During the write operation, the transistor is off. When current is passed through the write lines, an induced magnetic field is created at the junction which alters the polarity of the free layer. In order to change the polarity of the free layer, both fields are necessary. Only the bit in which the current is applied in both the hard and easy axis will be returned. The other bits will remain in half select. Now that we have learned how MRAM works, let us explore how the magnetoresistive element of MRAM can be used for logic computing. The input lines A and B here are operated with positive or negative currents of equal magnitude. The third input C is needed for the rotation of the two magnetic layers. This is a two-step procedure, the first one being presetting the MR followed by the logical operation. Now, let us see an example of logical computing of an MRAM through a simple example of AND gate. Before the logical operation, the system is set to an anti-parallel configuration by applying 0 at both inputs A and B. This corresponds to an output 0. A and B can be addressed independently with a 0 or a 1. The direction of magnetization remains unchanged if a 0 is applied at both inputs A and B. The same is applicable for a 0 and 1 at the inputs. The magnetization of an upper layer can only be switched by applying a logical 1 at both inputs A and B. This corresponds to an output 1, and this is how a basic AND gate functions. MRAM technology uses the spin-torque transfer property, which is the manipulation of the spin of electrons with a polarizing current to establish the desired magnetic state of the free layer to program or write the bits of a memory in an array. The spin transfer torque MRAM or the STT MRAM provides a significant reduction in switching energy compared to the toggle MRAM and is highly scalable, enabling high-density memory products. This third generation of MRAM technology uses a perpendicular MTJ. This provides a high perpendicular magnetic anisotropy, which provides long data retention, smaller cell size, greater density, high endurance, and low power. Now that we have learned how MRAM works, let us explore how the magnetoresistive element of MRAM can be used for logic computing. The input lines A and B here are operated with positive or negative currents of equal magnitude. The third input C is needed for the rotation of the two magnetic layers. This is a two-step procedure, the first one being presetting the MR followed by the logical operation. Now, let us see an example of logical computing of an MRAM through a simple example of AND gate. Before the logical operation, the system is set to an anti-parallel configuration by applying 0 at both inputs A and B. This corresponds to an output 0. A and B can be addressed independently with a 0 or a 1. The direction of magnetization remains unchanged if a 0 is applied at both inputs A and B. The same is applicable for a 0 and 1 at the inputs. The magnetization of an upper layer can only be switched by applying a logical 1 at both inputs A and B. This corresponds to an output 1, and this is how a basic AND gate functions. MRAM has a potential in all memory applications in these mentioned devices. In addition to the application of MRAM as a replacement for EEPROM and flash memories, especially for application where radiation hardness is required, MRAM can also be utilized as a gap memory when used with flash or EEPROM. By using an MRAM buffer, the write speed could be greatly improved, especially in burst modes, and the most frequently used addresses could be replaced with MRAM word addresses, thus extending the life of a memory system for a given application. Finally, the storing of used data for word addresses could be done in MRAM, once again extending the life of the system. To conclude, with numerous competitors in the field, there has been a reluctance to publish results. But it is clear that MRAM has the potential to be as fast and dense as DRAM with the additional advantage of non-volatility. Compared with flash and EEPROMs, MRAM writes much faster and does not deteriorate with millions of write cycles. MRAM has also been an ambitious IBM research project comparing the high density of DRAM and the high density of SRAM. Integrating silicon PM junctions with submicron MJT produces a system whose packing density is dominated not only by the active memory cell size, but by the 500 nanometer minimum dimension needed by the lithographic technology to integrate the silicon subsystems. In this presentation, we covered the concept of MRAM. We compared MRAM with the other non-volatile memory technologies, and we also discussed at depth the architecture of MRAM, the read and write process that goes in MRAM, and the applications of MRAM in the industry. Any questions? Thank you.